Time dilation is one of the most misunderstood ideas in physics, not because it's mystical, but because it contradicts everyday intuition. We feel time as constant and universal, yet the universe does not agree. Here is what time dilation really means and why time genuinely moves differently in space. The core idea in plain terms: time is not absolute. It does not tick at the same rate everywhere for everyone. How fast time passes depends on 1. How fast you are moving, 2. How strong gravity is where you are. This is not perception or illusion. It is a measurable physical effect confirmed by experiments, satellites, and modern technology. Time dilation from motion. Special relativity. This comes from Einstein's special theory of relativity. The key principle: the speed of light is constant for all observers, no matter how fast they are moving. To preserve this rule, the universe adjusts time and space themselves. What happens if you move very fast relative to someone else? Your time slows down compared to theirs. Your clock ticks more slowly. Biological processes slow down with it. This effect becomes noticeable only at speeds close to the speed of light. A concrete example: imagine two identical clocks. One stays on Earth, one travels on a spaceship at 90% the speed of light, then returns. When reunited, the traveling clock shows less time has passed. The traveler is younger than the person who stayed behind. This is not theoretical. Atomic clocks flown on jets and satellites confirm this effect precisely. Why this happens: time and space are linked into a single structure called spacetime. When you move faster through space, you move slower through time. Think of it as a fixed budget. More motion through space gives less motion through time. Time dilation from gravity. General relativity. This comes from Einstein's general theory of relativity, and it's even more surprising. The key idea: gravity is not just a force, it is the curvature of spacetime caused by mass and energy. The stronger the gravity, the more spacetime curves, the slower time passes. What this means: a clock closer to a massive object ticks more slowly than a clock farther away. This effect happens even if nothing is moving. Examples: time passes slightly faster on a mountain than at sea level. Time passes faster on GPS satellites than on Earth's surface near a black hole. Time slows dramatically relative to distant observers. Again, this is not philosophical. GPS systems must correct for gravitational time dilation or they would drift by kilometers each day. Why space affects time? Space and time are not separate things. They form a single fabric, spacetime. Mass and energy bend this fabric. Motion stretches it. When spacetime bends or stretches, paths through time change. Different observers experience different rates of time. So when people say time moves differently in space, what they really mean is, the structure of spacetime is different there. Common misconceptions: time dilation is just perception. False. Clocks, chemical reactions, and aging itself are affected. It only matters at extreme speeds or black holes. False. The effect exists everywhere, just usually too small to notice. There is a single real time. False. There is no universal cosmic clock. Each observer carries their own valid time. The deeper meaning: time dilation reveals something profound about reality. Time is not a background stage. It is part of the physical universe. It responds to motion and gravity just like matter does. The universe does not run on a single timeline. It runs on many interwoven timelines, each shaped by speed and gravity. Why this matters: without time dilation, GPS would not work, modern physics would collapse, our understanding of space, energy, and causality would be wrong. Time dilation is not a weird side effect of equations, it is a fundamental feature of reality. In one sentence: time moves differently in space because time is woven into spacetime, and spacetime is shaped by motion and gravity.